Hello, in this session 5.6, we will learn how to take measurements of joint orientation, joint frequency, and RQD. You should study this session together with sessions 3.1 and 3.2 of this course on rock mechanics principles. Methods of measuring joint orientation, frequency, spacing, and RQD, and other joint geometrical properties are outlined in the suggested methods for quantitative descriptions of discontinuities in rock masses of the International Society of Rock Mechanics. In this session, we will focus on how to measure joint orientation, joint frequency, and RQD at rock face and on rock cores. The first part is on how to measure joint orientation. We will use a geological compass to obtain the dip direction and the dip angle of a joint plane. On the right, we can see the typical geological compass. It has a flat lid whose inclination angle can be measured. The compass main body can be leveled and it can measure the dip direction to the north. When we want to measure the orientation of a plane of the joint, say exposed at a rock face, we simply place the lid plate fully against the joint plane. In this way, the lid plane has the same orientation as the joint plane. By adjusting the compass body, and we can level the compass by making the leveling bubble to the center. The reading on the compass is the dip direction of the joint plane. The inclination angle of the lid plate is in fact the dip angle of the joint plane. If you have an electronic compass, you will still need to do the same in order to get the orientations, except that the readings are given by display digitally, as shown on the lower right photo. At the site, we often need to take many measurements. You just need to repeat the measurements again and again on selected joint sets or on all the accessible joints. To take the measurements on orientation is quite straightforward. To report the measurements, we need to include A. Set information, such as location, lithology, anisotropy, set conditions, joint conditions, and of course, photographs of the rock face. B. Measuring information, such as the date, the tools used, the number of measurements, whether measurements are taken randomly or on a specific joint set. C. Tabulated measurements of joint dip direction and dip angle. And D. Further analysis using spherical projection method if required. We will learn about hemispherical projection method in the next session. Now we come to the measurements of joint frequency and RQD at rock face. The rock face can be an outcrop, a quarry or open pit wall, or excavation phase in underground tunnel or mine. On those rock faces, we can measure joint orientations as we just learned. We can also measure joint geometrical distributions, including frequency, spacing, and RQD. The rock quality designation, RQD, is to present the fracturing degree of the rock mass. To start with the measurements, we fix a straight line on the exposed rock face and measure and record the length of the line. For example, 50 meter or 100 meter or 20 meter. The simplest and the quickest way is to count the total number of joints intersect by this particular line. You just count a number, say 45 joints within this particular line of 20 meter. We can also measure the spacing between each two adjacent joints, but that will take a bit of time because you're measuring each sections between two joints. Or you can take direct measurements on RQD, as we learned how to compute RQD in the formula before. Of course, with modern technology, we can also use photogrammetry techniques to measure the geometrical distribution of the joints, and then from there compute the frequency, spacing, and RQD. Now let's stick on with the simplest way, that having counted the number of joints along the measurement line, and also having the length of the line, then we can compute the joint frequency, which is defined as the number of joints per unit length. It is simply the measured joint number divided by the measuring length. The average spacing of the joints is the reverse of the joint frequency. That is simply the line length divided by the joint number. We learned in session 3.2 that RQD can be estimated by the equation RQD equal to 110.4 minus 3.68 lambda, where lambda is joint frequency. For most cases, if the joint frequency lambda is between 6 and 16 per meter. If lambda is smaller or larger than 6 and 16, then we can use the exponential equations, which are shown here. Reporting of the site measurements of joint frequency, spacing, and RQD will need to include A. Site information, again, location, lithology, anisotropy, rock face condition, and of course photographs. B. Measuring date, number of measuring lines, orientation of the measuring lines, whether it's horizontal or inclined. C. Tabulated measurements of joint number for each line. And again, you will have a number of lines to be measured. D, calculated joint frequency, spacing, and RQD for each line, and probably also the average for the whole rock face. It is a common and a basic practice that after obtaining cores from site investigation drilling, we do core logging. Core logging includes descriptions of rock and rock joints, including rock types, weathering condition, joint condition, joint orientation, joint surface roughness, and the other geological and geotechnical features. Another key logging activity is measuring RQD from those rock cores. The photo shows cores typically laid in core boxes from drilling. The core can be different diameters, and the most common size for site investigation drilling is the N size, which is around 50 mm. Many national and local geological offices have core libraries to keep the core of local rocks as geological records. For example, the photos on the upper right shows the cores in the core library of the Geological Survey of Victoria, Australia. To measure and calculate RQD on cores, we normally mark a central line on the top of the cores. We then use a measuring tape to measure and record the length of all the core pieces whose length is greater than 10 cm. Remember, we do not need to measure short or broken pieces that is less than 10 cm. We do that for each rounds of cores in the core box. As we have learned in section 3.2, RQD is the sum of the lengths of all the cores that have lengths equal or greater than 10 cm divided by the drilling length. This is to refresh on the calculation of RQD. Equation for computing RQD is given here. RQD equals to the sum of the lengths of cores longer than 10 cm and divided by the drilling length. Here, each Li must be equal or greater than 10 cm. L here is the drilling length. It can equal to the total core length if all the cores are recovered from drilling. Sometimes, when there are fault zones or filling materials, part of the cores can be lost in the drilling operation. Core loss generally represents that particular section is very fractured materials such as fragments or soil fillings. RQD should be calculated to the nearest 1%. There is really no need to go to decimal places in practice. As I mentioned before, typically RQD is calculated for each core log. On the core log sheet, measured RQD values are required to be shown. For complete RQD measurement report, we needed to have the general information on calling location, date of drilling, lithology, anisotropy, joint types, and the conditions. We also needed to record the date of measuring the RQD, the core box references, and the core photographs. RQD values can be presented in a tabular form for each column and for depth range. If required, we should also produce the RQD distribution histogram along the depths for each borehole. This is the end of the session on joint geometrical measurements, covering orientation, frequency, and RQD. Thank you, and see you at the next session. We will talk about hemispherical projection method. Goodbye.